Guys, today's video is on special functions, specifically piecewise functions and also the greatest integer function. Piecewise functions is made up of two or more functions, each with its own domain. Let's look at number one, evaluating through piecewise functions. So we're given f of x, which is just like y, is this function if x is less than -2, but it's 5x plus 3 if x is greater than or equal to -2. Find each value. So letter A says find f when x is -5. You're not going to plug -5 into both of these functions. You're going to plug it only into the function where your domain includes -5. In this case, it's this one because x is less than -2, so -5 is less than -2. That means we're going to take the -5 and plug it into the top function. Get 25 minus 1, which is 24. Let's look at letter C. Here, f of x is 7, f of 7. We're going to plug that one into the second function because 7 is greater than or equal to -2. So it applies to the second function. Plugging in 7 in for x, we get 35 plus 3, which is 38. Let's move on to another piecewise function in number 2. This piecewise function is made up of 3 different pieces. The first piece is everything less than -4. The second piece is everything between -4 and 1, not including those. And the third one is everything greater than or equal to 1. Let's do B. So here -1 applies to this middle function because it's between 1 and -4. Plugging it in for x, we get 1 minus 1 equaling 0. Write down what questions you have on evaluating the piecewise functions before we get to the graphing part. Okay, number 3, we're going to graph each piece first, and then we're going to find the domain and range. I'm going to do this one in red here. You want to graph f of x equaling x. So I'm just going to write it as y equals x, same thing, if x is less than or equal to -3. The way you do this is you just graph the normal function. So here is my y equals x graph, but I'm only going to graph it from less than or equal to -3. I'm going to erase everything that's not -3. So let me just redraw it. 1, 2, 3, close circle going down. So at -3, it starts. Close circle again because of the equal to sign. Then let's graph this function, y equals -2x plus 1, only starting at -3, but going in the positive direction. Let me show you what the graph normally looks like. If you did rise over run, it would kind of look like this, and you would connect all the dots. However, we only want it starting at -3, and that's this top dot right here. But since it's not a closed circle, we're going to put an open circle at -3, and then you're going to graph everything greater than it, which is just like that. Now let's look at the domain and range for this graph. For domain and range, you're going to do the whole thing as one graph, not each one separately. Left to right for domain is all real numbers, or -infinity to +infinity. For the range, the lowest to the highest, the lowest is -infinity, And the highest that this graph goes to is 7, open circle. Or you can write it like this. This also works. You can write everything less than 7, and it's y because it's the range. Both of those work. Let's move on to another one. 7's a good one because it has 3 pieces and a little bit of everything. Let's graph this in 3 parts. Let's graph y equals negative 2x, or excuse me, positive 2x. Let's see what that looks like when x is less than or equal to negative 2. The graph normally looks like this. Doing a rise over run of 2 over 1. But we only want it for less than or equal to negative 2. So I erase all these, and I start at negative 2. And it's going to be a closed circle because of the equal to sign. Everything going that way. Next, let's graph this green one. That looks like y equals negative x minus 1. I'm flipping it around so it's in slope-intercept form, but only between negative 2 and 4. Let's graph to see what it normally looks like. A negative 1 y-intercept with a negative 1 slope, but we only want it from negative 2, erase these, to 4. 1, 2, 3, 4. So we don't need these also. And on the endpoints at negative 2 and positive 4, they are open, just like that. And we connect the line. There you go. Last one. This looks like y equals negative 3. And you do that for everything bigger than 4. The normal graph of y equals negative 3 looks like this. You go down to negative 3, and you make basically a horizontal line across, but we only want it greater than or equal to 4. Here's 4. 1, 2, 3, 4. Closed circle, because of the equal to sign, and everything greater than it, just like that. Let's look at the domain and range now. The domain for this graph, if we look left to right, it's good all the way over here because this line goes on forever that way. Over here at this point at negative 2, it's still fine because I have a closed circle. It's good in the middle. Over here, it's still good because I have a closed circle, and it's good on forever that way. Domain's all real numbers, or negative infinity to positive infinity. The range from lowest to highest, it's good all the way down here. It's good all the way up here. Keep going, keep going. It stops. There's nothing above 1. So you could say negative infinity to positive 1, the parenthesis, or you can write, if you like set notation, y is less than the positive 1. Let's quickly move to the greatest integer function. This function is written as f of x, and you put kind of like equals 2 brackets with the x just like this. So this symbol means the greatest integer. Less than or equal to x. In short, this means that it will always round to the value down to the nearest integer. It's also frequently called a floor function. Let's look at a couple examples. So if you have f of 7, that means you're plugging 7 in for the x. So you round down to the biggest integer, which is already 7. For b, you take 2.3 and you plug it in. So you round down to the biggest integer, so that equals 2. It's a little more confusing when you have negatives. If you're rounding down from negative 4.8, think about that for a second. You're actually rounding to negative 5. So it's a little opposite for the negative numbers in this floor function. Let's look at some more examples. Peek at what this graph looks like. I'm going to quickly make a table on the left side with my inputs and outputs. So I'm going to input a bunch of x's and output to see what the y's are. And then we're going to talk about the graph. So I inputted 0, got 0, inputted 0.25, rounded down to get 0. Same thing with this. If I input 1, it's still 1. If I input 1.5, rounds down to 1. Input 2, you get 2. Input 3, you get 3. Input 4, you get 4. Let's look at the graph now. So at 0, I got 0, close circle. But if I input 1, I get 1. If I input 2, I get 2. If I input 3, I get 3. If I input 4, I get 4. If I input 5, I get 5. But you're not going to connect a line and make a diagonal line. Here's what it's going to look like. If I inputted 0.25 or 0.5 in the middle here, or 0.75, I still get 0. So it actually goes all the way to 1, but as soon as I reach 1, it jumps up. So it's an open circle. Same thing here, 1.5 all the way to 1.9. As soon as it reaches 2, it jumps up. Same thing here, as soon as it reaches 3, it jumps up. So you're going to put open circles, just like that, continuing the pattern upward. The same thing works for negatives. If I input a -1, I would get -1, but it would follow the same pattern going down using the floor function. You can even check by inputting, let's say inputted 1, 2, 3, let's say like -3.5, you would get the -4. Okay, this is the general pattern of a greatest integer function. Let me scroll to this graph real quick. Okay, there we go. So domain and range. The domain of this function goes on forever to the left and forever to the right. It looks like there's gaps, but there aren't because we have closed circles wherever there's an open circle. So we say the domain is all real numbers. The range, though, we go bottom to top. The graph only appears at integers. So what we say for integers is the letter Z. It's only at positive or negative whole numbers. Let me know what questions you guys have on the greatest integer function. We're going to do a couple more examples in class. I don't want to make this video too long. Let me know what you have questions about piecewise functions or greatest integer functions, and see everyone next time.